Hello. So I wanted to help you out with number 7. Number 7 says a body is thrown downward with an initial speed of 20 meters per second. So this object has an initial velocity. I'll just draw an arrow to show that it has an initial velocity. And then it's going to speed up as it falls. So I'm going to draw my arrows getting longer. And it's going to travel bigger and bigger distances each second. And it looks like the initial speed is 20 meters per second. I'm going to make down my positive direction. So I'll draw a number line next to this. And I'll have my object starting from 0 meters just because there's no initial position defined. So I'm going to make down my y direction measured in meters. And let's see what we can figure out. Well, first of all, if down is positive, then my position time graph is going to look like this. My velocity time graph should look like this. Is that correct? That's actually a really common error. Try to figure out what's wrong there. Notice the initial velocity is 20 meters per second, so I actually need to shift this line up a little bit to account for that. Okay? But our position time graph, the slope still just gets steeper since the object's speeding up. I should probably start my slope a little bit steeper just to show that. So I can take this line and actually start it out a little bit steeper, something like that, so it doesn't start flat, horizontal. That would show that my initial velocity is 20 meters per second downward. And then my acceleration graph really is no different than the other problems. My acceleration due to gravity is 10 meters per second per second. So let's put units everywhere. So we know what our numbers are measured in. All right? And then I suppose I could take this area, and that's 10 times t. That must be my change in velocity. And this area here is now not a triangle. And that's what makes this group of problems much harder. You can look at it two different ways. You can look at that green shape, this green shape here, as a whole. And you can look at this as a trapezoid, where this side was 20. This side was t because we didn't know it. And this height was 10t. Actually, that's incorrect. That height is 10t plus 20. So that's one way you could look at it. Now, we can't actually solve anything more in this problem because we don't have any additional information. So what I'm going to do is I'm just going to copy all of this stuff to the next slide because I have a feeling that we could use it there. So I'm going to group all this together, and then I'm going to copy it, and I'm going to go on to problem 8. Okay? Edit, paste. So I'm betting that this will help me with problem 8. Now I didn't want the 7 to go with it. Why don't I just move the 7 above? There we go. That looks pretty good. So now if we know, it says we know that this object falls for 4 seconds, but it's thrown down with the same initial speed. now that I know t, I can find things. Okay? So let me erase this. Actually, I don't need to erase that. Let me bring that back. I know that this is going to be 10 times 4 because I know this is 4 seconds. This is 4 seconds. So that means that's 4 seconds. That means this is 4 seconds, right? So 10 times 4 is 40 plus 20. That makes this height 60, okay? So, and our change in velocity looks like it's going to be 40 meters per second. And our displacement looks like it's going to be 60 meters. No, that's incorrect. The 60 meters per second is the height from here to here. Our 40 meters per second is our change in velocity. Well, we started at 20. Therefore, our final velocity, if we add 40 meters per second to our 20, we should get 60 meters per second. Okay? So this height here is 60. So there's two ways of solving this part here. We have a trapezoid. We can find the area of a trapezoid. Or we can break this up into a rectangle and a triangle. So I'll do it both ways. So again, we have a shape that looks like this under our velocity time graph. Now, this height was 20. This total height was 60, right? And this was 4 from here to here. So if we were going to take this area, again, this was a velocity time graph, so the area is our displacement. We just take the average of this height and this height and multiply by the time. Okay? So it's the average of the velocities times the time. And that should make sense. Since the two bases of this trapezoid are different heights, some people find it's easier if we tilt our shape. So I'll draw it that way for you. So if I tilt this sideways, sometimes that makes it easier for people to see. I tilt this thing sideways, right? Move this up a little bit. There we go. You'll see that this is 4, this is 20, and this is 60. So we're just averaging this number and this number. After all, if this was a rectangle, we would just do this amount times the width, whatever the width is. But since there's two different widths, two different bases, we just average the 20 and the 60 and multiply by 4. So let's finish that. Average of 20 plus 60 meters per second times the time. So we got the average of the velocities times the time here. And if you add 20 and 60, you get 80. Cut that in half, you get 40. So this is going to come out to be 40 times 4, which means our displacement is going to be like 160 meters. And our units check out, since these two velocities are meters per second times seconds, that gives us an answer that's in meters. Okay? Now I could do the same thing, just using sort of a different approach. Again, this is a velocity graph, the velocity time graph, that looks like a trapezoid, right? So the shape can be broken down into a rectangle and a triangle right here. Now, this height of the rectangle was 20. The length or width was 4. So this area in the middle is 20 times 4, which I think is 80. So that's 80 meters area. And then the triangle, the change in velocity in this problem was 40. So that's the triangle's height. And the width was 4. So 1/2 40 times 4 is the same as 20 times 4, which again is also 80 meter area. We add these up, and we should get the same thing we got using the trapezoid equation, which was 160 meters being our displacement. So the problems do get a little bit harder when there is an initial velocity, the object isn't released from rest, and it makes sense that the object will actually travel a further distance since it already has a velocity at 0 seconds. It's already moving. So it turns out to speed up 10 meters per second faster each second, but since it's already moving, it's going to go a lot farther than if we had just dropped this object from rest and it fell for 4 seconds. This number is significantly larger simply because our object already had an initial velocity. Anyway, I hope this helps you figure out some physics, and thanks for watching. Have a good day.